Hello guys, this is Csaba Hős and this is our first online fluid machinery class. What we are going to do today is we'll learn how to build up a pipeline characteristics and how a pipeline works together with a pump. Okay, so before we start doing this, let's have a look where we are. So far what we did, we explained and derived Euler's pump equation and velocity triangles. So we are familiar with both the axial and radial impeller velocity triangles. We know how they are composed of three different velocities, that is relative velocity, absolute velocity, and circumferential velocity, and how the different components of the axial velocity are linked to the head and flow rate of the pump. We also know how to use dimensionless numbers, so notably the flow number and the pressure number. We derived a specific set of equations that will explain and predict how the change in the revolution number affects the head and the flow rate of the pumps. We call these affinity laws. And we also understand the difference between the theoretical and real performance curves. Okay, so we are aware of the different types of losses within the pumps. What we are going to do today, we will learn how the pump and the pipeline work together and how to predict the pipeline characteristics. Okay, so consider the following figure. This is a very simple pipeline system. We have a suction side reservoir, we have a pressure side reservoir. So what we want to do is basically we want to convey flow from this to this. Okay, so it's very simple. We have to pump the fluid from this tank to this tank. Now, as you see, both of them generally can be pressurized. So the pressure above the water level in tank 1 is P1, the pressure above water level in tank 2 is P2, and there is also a geodetic height difference between them. So one of them is located above the other one. Neither of these are necessary, so you can very often, in case of water distribution system, both of these pumps are not pressurized, so both P1 and P2 are zero, that is ambient pressure. And it's also not a necessity that there is a height difference between them. Okay, but this is a general case. And then the two tanks are connected by this pipeline. The pipeline consists of straight pipe elements, like this one here, and elbows and fittings, like these ones here. Okay, and then of course somewhere in between there is a pump. Okay, so by definition what we said is that the Bernoulli enthalpy, the head of the pump, is the change of the Bernoulli enthalpy between the pressure side and the suction side, okay? The Bernoulli enthalpy being the sum of the pressure, the kinetic energy, and the geodetic height. So, to put it simple, what the pump does, it changes the fluid's energy, and this energy change is the head. We can also write a Bernoulli equation from the suction side tank water level up to the suction flange of the pump, so up to this point. So that is P over rho G plus Z1. We don't have a kinetic energy term here because we assume that on the surface of the water the velocity is negligibly small. And this equals the Bernoulli sum here, the Bernoulli enthalpy at this point, plus something that we call the head loss of the inlet piping. So this is simply the pressure loss, the pressure drop due to the internal friction of both the fluid and the friction between the fluid and the pipe wall, plus additional elements such as elbows, filters, etc. So all these things result in a pressure drop, and this is provided here in meters of water column. We can write a very similar equation for the pressure side. So basically the Bernoulli enthalpy at this point is the same as the Bernoulli enthalpy at the outlet point, plus again the losses here. And if you put these things together, so for instance, you observe that you have this term here. So in the head equation, you replace this term by the right-hand side of this equation. And you also notice that this term is exactly the one here. So you replace the green terms by this minus the suction side, then you will get this equation. Okay, this is very important, and we'll have a closer look at it. So we have several terms here. The first term is the pressure term, a pressure difference. So the pump needs to overcome the pressure difference above the two water levels on the suction side and pressure side. Obviously, if both tanks are open to the surroundings, then this term cancels. The next term is simply the geodetic height difference, so simply the fact that you want to elevate the water from here to here. The next one is a kinetic energy. Now this is interesting. At the outlet of the piping, there's a kinetic energy which was added by the pump, but we are losing this kinetic energy because then it's dissipated. But still the pump needs to add this energy. And finally we have the pipe frictions, okay, here. So this is what the head of the pump is, what we need for a given flow rate. And now we will have a closer look on how to estimate these terms, okay? So that is, again, the frictional pressure drop on the suction side of the pipeline system and on the pressure side of the pipeline system. Okay. So the frictional head losses for turbulent flow, which is usually the case in engineering cases, something we call a loss coefficient, zeta, times v squared over 2g. The velocity can be conveniently rewritten as the flow rate divided by the area. The flow rate is usually what we know. Okay, so zeta is the loss coefficient, q is the volumetric flow rate, and a is the cross-section of the pipe. Now for straight pipes, this term here, this zeta, is lambda times L over D, L being the length of the pipe, D being the diameter of the pipe, and lambda being the pipe friction factor. And so this is another factor, and then you get this number from the so-called Moody diagram. So this is the Moody diagram. This looks complicated, but it's not that terrible. On the horizontal axis, we have the Reynolds number. Okay, so velocity times diameter times density divided by viscosity. This is, if you like, the dimensionless velocity of the flow. On the vertical axis, we have this friction factor, which is very often denoted by lambda, but also sometimes it's denoted by F, friction factor. Okay, so both of them are used. Now what we see is that in this region, so as long as the flow is laminar, lambda is simply 64 over the Reynolds number. So surprisingly, no matter what the internal roughness of the pipe is or the pipe material is, as long as the flow is laminar, you will simply take the Reynolds number, you compute 64 over Reynolds, and then you get lambda. However, if you get beyond this region, so usually the number we say for laminar turbulent transition is 2300. Okay, so if you are beyond 2300, then the flow is turbulent and you have a bunch of curves here, and the parameter is the relative roughness. Okay, so how rough the pipe is, obviously the larger the roughness is, the larger the friction factor is. Okay, so this is the lowermost curve is the smooth pipe, and then it's increasing. So the way you use this curve is as follows. You say that, okay, let's assume I have an cast iron pipe. So the epsilon, the roughness is approximately usually 0.15 millimeters. Then you compute the relative roughness, so you divide this number by the diameter, and then you get, okay, let's say you get this number. Okay, so this is your relative roughness, and then you have the velocity, the pipe diameter, your fluid, and let's say that this is your Reynolds number here, and then you simply have a look what the lambda value is for this Reynolds number. Okay, so this is how you use the Moody's diagram. There are also standard correlation equations, which, for example, you can find on this Wikipedia page. Okay, so this whole business, this whole Moody diagram is about getting the friction factor. Okay, and once again, to compute the head loss of a straight pipes. Okay, so lambda comes from the Moody diagram, then you compute zeta, you plug it to this equation, and then you get the head loss in meters. Minor losses, so elbows, filters, valves, etc. are coming from the tables of the manufacturers. So for example, you would see something like this. I have, let's say, a gate valve which is fully opened. In this case, the number will be 15. 0.15, sorry. So the rest of the numbers are coming from tables. Good. So now we know how to compute all these terms, okay? So P1, P2 are simple numbers. Velocity comes from the flow rate. Z2, Z1 are geometry, and we already know how to compute the frictional losses. Okay, so now what you can see is that the red terms, so the pressure difference and the height difference, are not depending on the flow rate. So they are independently there no matter what the flow rate of the pump is. So clearly the pressures will not change, and also the geodetic height difference will not change. So there is a term which is independent of the flow rate, but there are the green terms which all depend on the velocity. That is, they depend on the flow rate. So the pipeline characteristic will be something like this. You have something we call a static head, which is essentially this A number here, then plus B times Q squared, which is this term here. Okay, so this is what we call a pipeline characteristics. The larger the flow rate is, the larger the pressure difference you need to push that amount of fluid through your pipeline system. Okay, so this is the main idea, that the more fluid you want to push through this system, that is, the higher the velocity is, the fluid velocity is in your pipelines, the larger the pressure difference is that you need and the pump has to provide. And then you plot to the very same curve the pump characteristics, which is this. And when they intersect each other, that is something we call the operating point. Okay, so this figure simply means that if I plug this blue pump to this red pipeline, then this will be the flow rate. If I buy a smaller pump, whose characteristic curve is like this, then with this smaller pump, the same pipeline system, I'll have a smaller flow rate. And vice versa if the pump is larger. If you, for instance, if you change the height difference, so say that Z2 and Z1 will be smaller, the difference, then the pipeline characteristic will come here somewhere, and this is going to be your operating point, so now your operating point will be larger. Again, so if you decrease the height difference, that is A, the static head decreases, so your pipeline system will be something like this. Then, assuming that the pump is the same, you'll get a larger flow rate. Okay, as simple as this. Okay, so there are some things to do for you for this week. So first of all, please read carefully chapter 3 in the lecture notes. Okay, essentially the same things are written there. Make sure that you understand how to compute the Reynolds number for pipes. Okay, this is very important. Make sure that you can use Moody's diagram. This is also important. And also, please, I did not mention it in this video lecture, but what is the kV value of a valve? Okay, this is an important quantity. It's used all around in the industry. So what is the kV value of a valve? Actually, I'm explaining it in equation 3.3 of the lecture notes. Okay, so that was it for today, and I will see you next week with the next material. Bye-bye.